Hello, and welcome to the lecture on section 4.1. Today we're going to talk about exponential functions. Let's start out with the definition. The exponential function with base a is defined for all real numbers x by f of x is equal to a to the x, where a is greater than 0 and a is not equal to 1. Now these two conditions are very important because a needs to be greater than 0. Otherwise, we have a sort of weird function that has a lot of discontinuities. For instance, suppose that we have a negative 2 to the x power, right? So let's say that this is our f of x. So then when we see negative 2 to, say, the 3 halves, this is undefined because this is the same thing as saying negative 2 to the third power, but we take the square root. This. So we end up with taking the square root of a negative number. Now, when we're talking about real numbers, this is not possible. So this actually causes a lot of problems. Also, if we had, say, negative 2 to the first, this is fine, negative 2, but negative 2 to the second is 4. We no longer have the negative, right? We have a positive instead of a negative. So if we were trying to graph this, it would alternate between positive and negative on the integers, and then there would be a lot of discontinuities between the two integers. Between any two integers, there'd be a ton of discontinuities for any sort of even root. The other condition, a is not equal to 1, is a bit more because a equals 1 is not really interesting. It's just a lot. So suppose that we have the function f of x is equal to 1 to the x. Then no matter what x is, this is always equal to 1. So we would end up with just f of x is equal to 1. These two are the same. This is why we exclude any negative values. We exclude a equal to 1. And we also exclude 0 for the same reason as we exclude 1. It's also not interesting. 0 to any power other than 0 is equal to 0. Let's do an example really quickly here, just to get a little bit more familiar with exponentials. So suppose that we have f of x is equal to 2 to the x. So we have this. Now I want you to find f of 3, f of negative 3, and f of 1/3. Now remember, if we're replacing x with 3, that means we replace this x with 3 as well. So we would end up with 2 to the third power for this first one. All part A, part B, and part C. So for part A, we have 2 to the third. This just means 2 times 2 times 2, right? Remembering that a to the n is equal to a times a times a n times. So there's n a's here that are all being multiplied together. This is when n is an integer. And when we have a rational or an irrational number instead of an integer, it becomes a little bit more complicated, but it's unnecessary to go over those for right now. So suppose we have this, we end up with 2 to the third is equal to 8. F of negative 3 now. So we plug in negative 3 for x, and we get 2 to the negative third power. Right, now what does this do? Now try to remember what a negative does in the exponential. So if we have a negative exponent, what happens? Well, if you remember correctly from chapter 1, this negative will take the entire term and change it from being in the numerator to the denominator, or vice versa. If this was, say, in the denominator, then this entire term would move to the numerator because we have a negative exponent. So this being in the numerator already, being divided by 1 like this, then we would have 1 divided by 2 to the third power, which, as we saw above, 2 to the third power is 8, so we end up with 1/8. So notice that if we have a negative exponent, we end up with a fraction like this. That is, if 2 is a whole number that's bigger than 1. Now suppose that we have the 1/3. Now I think we already talked about this, but if we have 2 to the 1/3 power, this is just saying the cube root of 2. So we have this actually defined for rational numbers already as exponents and radicals. So this would be 2 to the first power under a cube root. If we had say f of 2/3, then this would look like this. 2 to the 2/3, which is equal to 2 squared, but we take the cube root, which is the same thing as the cube root of 4. The next thing I want to talk about is graphs of exponential functions. Now, as we go over some of these, I want you to think about what the domain and the range of these graphs are going to be. Try to figure them out before we get to the next part where we explain what the domain and range will be. Let's start with an example here. Suppose that we have f of x is equal to 2 to the x. If we just plot a few points, then we can figure out what this will be. Let's say we have x here and y is equal to 2 to the x. So if x is equal to -2, -1, 0, 1, and 2, we can plot some of these points. If it's -2, then we have 2 to the -2. Now, if you remember from the previous section when we had 2 to the -3, we just rewrite this as a fraction because of the negative exponent. So recall that the negative exponent actually moves this entire term into the denominator because it's currently in the numerator. So this is going to end up being 1/4 at -2. At -1, it would be 1/2. 2 to the -1 would just move it into the denominator. Then you would have 1 divided by 2 to the first power, which is just 1/2. Now 2 to the 0 is just 1. Anything to the 0 power other than 0 is equal to 1. So we will have the y-intercept here will be at 0, 1. 2 to the 1 is of course 2, and 2 to the 2 is of course 4. Let's go ahead and plot these. So at x equals -2, our y value is 1/4. So right about here. At x equals -1, our y value is 1/2. So that's going to be a little higher up. At 0, we cross 1, and then at 1, we have 2, and at 2, we have 4. So as you can see, we have sort of this trend here, where this is a weird bend. If we keep going farther and farther to the left, we'll keep having a more and more negative x value, which just means we're going to have 1 divided by 2 to a higher and higher exponent. So for instance, 2 to the -3 is 1 over 2 cubed, which is 1/8. 2 to the -4 is 1 over 2 to the 4th, which is 1/16, and so on. And this denominator is just going to keep getting larger and larger. So what ends up happening is as x gets closer and closer to -infinity, our y values are getting closer and closer to y equals 0. We end up with a horizontal asymptote here at y equals 0, the x-axis. Now on the right side, as you might notice, if we keep allowing x to get bigger and bigger, we're just going to get 2 to a higher and higher exponent. So this is actually going to go up to infinity as well. It's actually going to go up to infinity rather quickly. So it looks something like this, where we never actually touch the x-axis, but we get closer and closer to it for this function. Now try to think how this would differ from other exponentials. We're actually going to graph a few here. What I want to do now is plot f of x is equal to a to the x, where a is equal to 1/4, 1/3, 1/2, 2, 3, and 4. Just to give us an idea here. Let's start with f of x is equal to 1/4 to the x power. If x is equal to -2, we end up with 1/4 to the -2nd. Now, if you remember what that negative does is it flips the fraction if it's on the outside of the parentheses. If it's on a single term, it'll move that term to the denominator. We can distribute this x to be on the top and the bottom because it's we have division here. So if I plug in a -2, it'd be the same thing as 1 to the -2 in the numerator and 4 to the -2 in the denominator. Now that 4 to the -2 would end up moving to the numerator, so we would end up with 4 squared here, which is 16. 1/4 to the -1 will just be 4. 1/4 to the 0 power is 1. 1/4 to the 1 is, of course, 1/4, and 1/4 squared is 1/16. So we see what we have here with these 4 points. Let me plot these really quickly. Plot them in red. So -2, 16 is very high. I'm not going to plot that because it's too high for my chart. -1, 4. This point here. At 0, 1. At 1, 1/4 would be here. And then 2, 1/16 would be very, very close to the x-axis. Basically, it looks like it's on top of it from our view, but if we zoomed in, we could probably distinguish. So we would end up with something that looks like this, where this gets closer and closer to the x-axis on this side, but we never actually reach it. Now this is y is equal to 1/4 to the x. Now what I'm going to do, also in red, is plot the graph f of x is equal to 4 to the x. Now I want to do this in red specifically because it's related to the 1/4 graph. And we'll see how in a second. So if we have -2, -1, 0, 1, and 2 for our x's, and then y is equal to 4 to the x, we'll see what we get. So if I plug in a -2 here, I end up with 1/16. If I plug in a -1, I get 1/4. Plug in a 0, I still get 1. Plug in 1, I get 4. Plug in 2, I get 16. I want you to notice here that if I plug in a -2 for x for this graph, it's the same thing, the y value is the same, as if I plugged in a 2 for this graph. Why is that? Well, this and this are related because they are reciprocals of each other. So 1/4, if we take the reciprocal of 1/4, we would have 4/1, which is exactly 4. Now, remember what a negative exponent does. So if I had 1/4 to a negative value, negative whatever, a, then I would end up with 4 to the a power. So it would be the same thing as if I was plugging in a for this graph. F of x equals 4 to the x is exactly the reflection of f of x is equal to 1/4 to the x about the y-axis. We still have a point at 0, 1. And then at -1, we would be at 1/4. And then at -2, we would be at -1/16, which of course is still very close to the x-axis. If we plug in x equals 1, we end up with 4. 1, 2, 3, 4. At this point, so we would end up with something that looks like this. This is y equals 4 to the x. Now notice it's an exact reflection when you reflect about the y-axis. And that should make sense because if we replace x with -x, let's say that we have a to the x, and we replace x with -x, remember, a -x reflects it about the y-axis. This would be the same thing as 1/a to the x power. So this is reflected about the y-axis to this graph, and this graph is identical to this graph. So here, if we replace a with 4, we can see that a to the x here would be the reflection of this graph about the y-axis. I'm going to run through a equals 1/3 and 3 in blue, and then we'll do 1/2 and 2 in green. But I'm going to do these a little bit quicker so we save on time a bit. So if we have 1/3 for a, then we have 1/3 to the x. Plugging in a -2, we end up with 9. That would be way up here. We only have 6 tick marks, so I'm not going to draw that one. But at -1, we would have 3. So here is that point at -1, 3. This is for the 1/3 graph. 0, 1, of course. And then at 1, we would be at 1/3. Be just above this. And then at 2, we would be at 1/9, which would also be above this. So we would end up with something that looks like this. where it flips positions. Here on the left, it's lower than 1 over 4 to the x. On the right, it's higher. And that should make sense when you go through the y values. Right? Now, if we do the reflection, that would just be y equals 3 to the x. We would get an identical graph, but reflected about the y-axis instead. So we would end up with something that looks like this. Since y equals 3 to the x, all of these graphs will have a horizontal asymptote of y equals 0. Let's finish up with y equals 1/2 to the x and y equals 2 to the x. So if we have 1/2 to the x at -1, we would have 2. It would be here. At -2, we would have 4. At 1, we would have 1/2. And at 2, we would have 1/4. So we would end up with something that looks like this. This is y equals 1/2 to the x. And if we have y equals 2 to the x, we just have the reflection. So we would get this point, this point, this point, this point, and this point. So we would end up with something that looks like this. This is, of course, y equals 2 to the x. Now look at all of these graphs and look at what they have in common, and look at and try to figure out the domain and the range. Right? Now the domain should be pretty obvious. It was even in the definition. The exponential function with a base of a is defined for all real numbers x. What that means is that no matter what x is as a real number, a to the x gives a y value, which means that it's defined for every real number. The domain of this function will actually be all real numbers. For this function type will be all real numbers. So the domain of this function type will be all real numbers. All exponential graphs have domain all real numbers. But the range will be from 0, not including 0, to infinity. As you can see, all of these graphs will go up to infinity on one side or the other. And then on the opposite side, it'll go down towards 0, but never actually reach y equals 0. So our range is going to be 0 to infinity. Graphs of exponential functions. The exponential function f of x is equal to a to the x, where a is greater than 0, and if a is not equal to 1, has domain r and range 0 to infinity, excluding 0. The line y equals 0 is a horizontal asymptote of f. The graph has one of the following shapes. So we either have a graph that starts down here towards y equals 0 and goes up to infinity, crosses at 0, 1, or it starts close to infinity and comes down towards 0, like this. And again, crosses at 0, 1. Now, which one of these shapes has a less than 1, and which one has a greater than 1? Pause the video and think about it for a second. When you think you have an answer, unpause the video. This one will be a is greater than 1, and this one is a is less than 1. Now, we already know that a has to be greater than 0, so this would be in this form. It would be a fraction, a positive fraction, that's less than 1. But this should correlate to what we've seen prior. So if we look here, we can see that our a is less than 1, where it starts at infinity and comes down towards 0. Over here, we have a is greater than 1, where it starts towards 0 and goes up to infinity. So these shapes should be in line with that, and they are. Let's do an example here. Find the function f of x equals a to the x that contains the point 3, 1 over 27. So here there's a bit of information that we know, but is a little bit hidden. Here, find the function f of x is equal to a to the x. This is saying that we already know the form of the function. We know that it's an exponential. What we're trying to do in this problem is figure out what a is, because it will be of the form a to the x. I just need to know what a is. I also know that this point is contained in this function, which means that if the x value is 3, then the f of 3 value is 1 over 27. So let's go ahead and write that. F of 3 is equal to 1 over 27. Here. Now, if I just rewrite this form here, then I have that f of 3 is equal to a to the third. Now I know f of 3 is a to the third because it's this form. I also know f of 3 is 1 over 27. So these two things actually have to be equal. We end up with a to the third is equal to 1 over 27, and we just need to solve for a. We take the cube root of both sides, then we end up with a is equal to 1/3. So our function, f of x, is equal to 1 over 3 to the x power, like this. And I'm going to do one more example here. This one's more of a graph shifting. Transforming exponential functions. So suppose that we have f of x minus c like this. What does this do? This actually shifts horizontally if you remember. Now, depending on whether c is positive or negative, if c is negative, we would end up with, x plus something, so it would shift left. If c is positive, it would shift to the right. Now, what if we have f of x plus c, like this? It shifts vertically. Now again, if c is negative, we're shifting down. If c is positive, we're shifting up. But it does shift vertically. Now, for the stretching factors, or the shrinking factor, f of ax stretches or shrinks horizontally, depending on what a is. If it's greater than 1, then it shrinks. If it's less than 1, then it stretches. And then if we have a times f of x, we stretch or shrink vertically. Again, depending on what a is. If a is less than 1, then we shrink. If a is greater than 1, then we stretch vertically. All of these rules apply to exponentials because they apply to every graph. But in this case, we're going to apply them specifically to the exponential function. Graph f of x is equal to 3 times 2 to the x plus 1. So notice here, we have a stretching factor of 3. So we're going to stretch 2 to the x vertically by a factor of 3, and then we're going to move all of the points up by 1. So our parent graph in this case will be y equals 2 to the x. Let's go ahead and plot the parent graph. This would be y equals 2 to the x. Now what I want to do is I want to stretch each of these. What I want to do is I want to stretch the vertical distance by 3 for every single point. So instead of being at 4 here, I would be at 12. Instead of being at 2, I'd be at 6. Instead of being at 1, I'd be at 3, and so on. And that will be the graph y equals 3 times 2 to the x. Do that in blue. So again, instead of being at 0, 1, we are going to be at 0, 3. Here at negative 1, 1/2, we'd be at negative 1, 3/2, which is 1.5. And then instead of being at negative 2, 1/4, we'd be at negative 2, 3/4. There. And then 1, we'd be at 6. So the general shape of y equals 2 to the x is just a little bit stretched out now vertically. And the last thing that we're going to plot is the entire function, the one that we're looking for. Do that one in green. This one will be y equals 3 times 2 to the x plus 1. So I take all of my blue points and I move them up 1 unit. Now notice that I have a horizontal asymptote at y equals 0. So if we move every single point, then that guideline is also going to move. The horizontal asymptote will actually move up 1. Let me go ahead and plot that first. It'll look something like this. Now, exponentials are kind of tricky in that they have a few unusual properties, specifically to do with stretching horizontally or shrinking horizontally and shifting horizontally. Now, I want to show you what happens here. Recall that a to the b plus c is equal to a to the b times a to the c. So remember, if we have the same base and we are multiplying, we just add exponents. So if I have a to the b times a to the c, all I need to do is add the exponents, and I would have my result. This means then that you can undo it as well. So for this particular problem, let's say that we wanted to figure out what the shift would be here. So let's say that we have y equals 2 to the x minus 1. Right? Well, what's happening? Well, if we break this up using this property, we would end up with 2 to the x times 2 to the negative 1, which is equal to 1/2 times 2 to the x. Our 2 to the x just stays the same. 2 to the negative 1 becomes 1/2. So if we shrink it by 1/2, then it's the same thing as if we moved the entire graph to the right 1 unit. This is actually an interesting property because we can rewrite a horizontal shift as a vertical stretch or shrink. Do another one. If you remember a to the b to the c power, this is equal to a to the b times c. So if we take a power to another power, you multiply those two exponents together and you put it on the base. So we would have a to the b times c is the same thing as a to the b to the c power. So now let's look at a horizontal stretch or shrink. So suppose we have the graph y is equal to 2 to the 3x. Now what this would do is it would actually shrink the graph horizontally by a factor of 3. But instead, what I'm going to do is rewrite this as 2 to the 3rd to the x. Now I have 2 to the 3rd written as a single term, all to the x power. Now 2 to the 3rd is the same thing as 8, so I can rewrite this as 8 to the x. So if we were to horizontally shrink the graph, we can rewrite it as 8 to the x. In this particular case, we can rewrite it as 8 to the x. So it becomes a completely different exponential, one with a higher base. Now, if this was, say, 1/2 instead, y equals 2, let's say 1/3 instead, 1/3 x. Now, this is a horizontal stretch. It would stretch the graph 2 to the x horizontally. Now, I can again rewrite this as 2 to the 1/3 to the x power, which would become the cube root of 2 to the x power. So instead of having a base of 2, now I have a base of the cube root of 2 as an exponential. So instead of stretching the graph horizontally, I can rewrite it as a completely different exponential. Now these are interesting properties that come up with exponentials. I want you to try a problem now. Graph f of x is equal to 3 to the x minus 2 minus 1. And the next thing I'm going to talk about is compound interest. Definition. The principal is the amount initially invested. Now, what I'm going to do right now is explain what compound interest is conceptually, and hopefully we get a better understanding of where the formula will come from. So suppose that we have our principal here, and this is a 10 by 10 square. This is our principal. Now, what compound interest is we take a percentage of this and then we add it back into the principal, so that when we take the percentage in the future, we're not only taking the percentage of the original principal, but also all of the interest that has accrued over every single time that we've compounded it. So let's explain it a little bit slowly here. So suppose we have this principal, and it comes time to compound our interest for the first time, assuming that our rate is 10%. So we'll take 10% of our principal, and we get this. This is 10% of this. It's 1/10. Now, what we do now is we add this into our principal, so that when it comes time to compound our interest a second time, we take 10% of this, but also 10% of the interest that we've already compounded. So as of right now, we have 10 by 10. So this is 100 squares, and then we have another 10 squares here, right? So when we compound again, we will take another 10% of the original. This rectangle is going to represent 10% of the original principal. But we also take 10% of the interest that has accrued. So we take 10% of this interest because it's already been compounded into our principal. So we would also have 10% of that, which is this little square here. So this would be 10% of this. So this 10% comes from the original principal. This 10% comes from this interest. And we would add all of this back into our principal. So we wouldn't, if we looked into our account, we wouldn't just have our principal. We would have the original principal plus the interest that was accrued after the first compounding period, plus the interest that had accrued after the second compounding period, which was not only 10% of the original, but also 10% of the interest that we had accrued after the first compounding period. Right, so all of this would be our money now. So we would have 100 squares, plus this 10 is 110, plus this 11 would be 121. So after each compounding period, we will be compounding more and more interest because our principal will be increasing multiple times. Let's try to look at this mathematically now, and we'll see if we can get a formula for this. Let's say that we have our principal, and we're looking for our future value here. We're looking for the amount after a certain number of compounding periods that we need to do. So after the first compounding period, we take a percentage of P. So we take our principal, we add the rate times this principal, whatever our rate per compounding period is. This would be how much we have as principal after the first compounding period. So this is the same thing as P times 1 plus R. So we've compounded our interest once here. If we didn't compound, this would be what we had. So if we haven't compounded any interest, we just have our original principal. If we've compounded our interest once, we would have P times 1 plus R, because it would be our principal plus a rate times our principal. Now let's compound a second time and see what happens. So now we take the current principal that we have, which is P times 1 plus R, and we multiply it by our rate. So we would take this is what we currently have, and we add the interest that has accrued on this principal, on this amount of money. So it would be plus P times 1 plus R times R, like that. Now these rectangular parentheses are unnecessary, but it would just be this. So we would have our rate times our current amount would be how much we're compounding plus the current amount that we have. So this would be compounding twice. If you can see, what I'm going to do is I'm going to factor out a P times 1 plus R because I have it common in both terms. Here's our first term. This entire thing is our second term. Notice that we have a P times 1 plus R, P times 1 plus R. So I'm going to factor that out. What will be left here is just 1. What will be left here is just R. So we'll end up with P times 1 plus R times 1 plus R. Now this 1 plus R comes from what would be remaining after we factor out that P times 1 plus R, which is the same thing as P times 1 plus R squared. So now this is our new principal. This is how much we currently have after compounding twice. Let's compound a third time and see if we can see a pattern. So we would take our current principal, the amount that we currently have, P 1 plus R squared, and we add the interest that we collect on this amount. So we multiply this by R and add it. P 1 plus R squared times R. This is representing the interest. This is representing the current principal that we have. So we take our interest that we earned on the current principal and we add it to the current principal to get to compound. Now, again, I'm going to factor out p times 1 plus r squared, and I get p 1 plus r squared. And what's left here, if I factor this entire thing out, is a 1. And if I factor out the p times 1 plus r squared, I'm left with an r. Which, of course, is then p times 1 plus r to the third, because 1 plus r squared times 1 plus r. Think of this thing as an object. I have this object squared times the same object. So I just add the exponents. I get a 3 instead of a 2. So notice, after each compound, 1, we have a power of 1, 2, we have a power of 2, 3, we have a power of 3, and so on, and so forth. And we can do this as long as we want, but we'll end up getting a certain formula. In a our very basic formula would be this. A of t is equal to p times 1 plus r to the t power. Now, I'm going to complicate this a little bit. And I'm going to replace my r with r over n, because I'm going to change a few things. This, currently, this would be compounding 1 time per year. But what if we wanted to compound 3 times a year, or 4 times a year, or 12 times a year? Compounding monthly, or every other week, 52 times a year, or every day, 365 times a year we're compounding. Well, then this formula doesn't really help us, because this formula can only be used when we compound 1 time per year. So we keep the definitions of our r and t, which I'll give you in a second, but we add a new variable, the number of times that we're compounding per year. And this is going to be our actual formula. A of t is equal to p times 1 plus r over n to the nt power. Now this n is going to represent the number of times that we compound per year. And this is the formula. It's the same form, it's just slightly different formula, because we have we can compound multiple times a year instead. Notice that if n is equal to 1, meaning we'd be compounding once per year, we would revert back to this formula. Let's formalize this a bit. Compound interest is calculated by the formula A of t is equal to p times 1 plus r over n to the nt, where A of t equals the amount after t years, p equals principal, r equals annual interest rate, that's the interest rate per year, n equals the number of compound periods per year, and t is the number of years. Let's do an example. Fresh Clovis invests 10,000 credits at a rate of 4% per year compounded monthly. Find the amount after 5 years. All right, so we're looking for the amount after 5 years. Note that we're looking for A of t, where t is equal to 5, because t is the number of years. So here we can say t is equal to 5. N is the number of compound periods per year, and we're compounding monthly. So we compound once per month, which would mean that we're compounding 12 times per year. So N is 12. Our rate is an annual interest rate, so it's an interest rate per year. So we look back here and we see a 4% per year. So our R is 0.04. And P is the principal, that's the initial amount invested, if you remember from the definition. So our principal in this case is going to be 10,000 credits, because that's how much he invested originally. And we're looking for A of 5. Figure out what A of t is first, and then we'll figure out what A of 5 is. So A of t will equal P, 10,000, times 1 plus our rate, 0.04, divided by n, 12, to the n times t, so 12 times e. This would be A of t. We're looking for A of 5. A of 5 would be 10,000. 1 plus 0.04 divided by 12 would be 0.003 repeated to the 12 times 5. Note that I'm plugging in a 5 for t. This is the same thing as 10,000. 1.003 the 60th power. So it ends up being 12,209.97 credits. I want you to try one now. Now this will be very similar to the problem that we just did. The Immune invest 20,000 credits at a rate of 6% compounded monthly. Find how much that investment is worth after 10 years. It's actually an identical problem to the one that we just did, so you just need to follow the same steps. All right, that's going to be it. I will see you all in the next lecture.